Hello, everyone. Today I'm going to present my work titled Decentralized DR Integration into Wholesale Energy Market via Mainfield Games. Third Order 2022 aims to enable distributed energy resources, for example, domestic PV panels and energy storage, to participate in the wholesale markets. The challenge is how can we ensure meaningful participation of small-scale prosumers who can both produce and consume electricity? The goal of the research is to automate aggregators or virtual power plants' participation in the wholesale market and to study the market outcome with a vast number of grid edge resources. First, this is an overview of our model. Besides the centralized generator and the transmission grid, we now have the small-scale prosumers who consume and generate electricity. Because they're small scale, we have to aggregate their information, their electricities to the virtual power plants with aggregators and communicate the aggregated information with the transmission grid so that system operator can solve the wholesale market and update the location marginal prices. So the model can be broken down into two parts. First, the wholesale market, which is basically an economic dispatch linear programming problem, which is to find the least generation cost to meet the demand and subject to some physical constraints. The dual values can be used to determine the location of marginal prices. And the second part is the aggregator, which consists of the hybrid approach of Mainfield game and Mainfield control, and I will explain this later. So the workflow of the model looks like this. First, with the economic dispatch, we solve and get the location of marginal prices. And each bus had the price, and each aggregator associated with that bus will will learn using reinforcement learning and get updated policies. The aggregator will distribute its policy to the associated prosumers, and each prosumer will act according to that policy, and the system will collect all the information and proceed to the next time step. So here, the reinforcement learning is actually a multi-agent reinforcement learning problem, which means more agents we have, the harder it is to learn. The remedy is to use the mean field to approximate the results. So what is the mean field? The mean field is that as population goes to infinite, each agent change of behaviors will not impact the overall distribution of the population, which is the mean field here. And it is actually a very good approximation to the multi-agent reinforcement learning problems, especially when the population is large. And then we can assume that we have infinite prosumers here. And the multi-agent problem is then reduced to the interaction between a single representative agent and the mean field. As I said before, the aggregators are taking the hybrid mean field approach. What does that mean? First, for the mean field game, given the LMP, each aggregator finds the best policy. So the mean field here is the location of marginal price, and the aggregators are actually competing with each other. And for the mean field control, it means that each aggregator's policy maximizes the total rewards of all its prosumers. The mean field here is the distribution of the prosumer states and actions, and the prosumers under the same aggregators are cooperating with each other. So again, under the same aggregators, prosumers cooperating with each other, but different aggregators will compete with each other. So next we need to set up the mean field game. So first we have the simulation time step, which is the real time t. And then each time t, we train each aggregator for t train steps, and we use tau to be the index here. And we have m prosumers in the games, and we also have aggregators, which are the representatives of the prosumers. And each bus has one aggregator just for simplicity. And each aggregator will maintain an LMP belief vector to capture the long-term price changes. The states of each aggregator, the representatives, are the current state of charge, and also there are other exogenous states such as the LMP belief, the hour of the day, and demand. And then they will take actions, which is the storage charging and discharging. And we set it from -1 to 1, which is the discrete action space. And each number represents the percentage of the storage capacity. So if it is a negative number, it is discharging from the battery and sell the electricity to the grid, and the positive is charging and buying electricity from the grid. Each step, the aggregator is earning some reward, which mathematically look like this, but it is basically just price times selling quantity, which is the selling revenue at the reward. And our policy is to find the best policy that gives me the most total rewards during the training, right? So here's the action, reward, and the policy is defined for each aggregator N. And as said in the beginning, we want to study the market outcome, which is we want to see if there is a market equilibrium here. And because it's mean field, so we are looking for a mean field equilibrium. So each mean field is associated with the location of marginal price. And with each LMP, we can solve a reinforced learning problem and get a policy pi. And with that policy, the prosumer will take actions according to the policy, and the mean field can evolve, and the simulation proceed to the next time step. So it looks like this. So at time step 0, we have mean field 0, LNP 0. With RL, we get a pi 0 at the policy. And taking the policy pi 0, we evolve to the mean field 1 with LNP 1, and then we get a policy pi 1 through reinforced learning. We do that again, and in the end, we will converge to this mean field star, LP star, and which with RL gets pi star. And with the pi star, the mean field evolves back to mean field star, and we still get a pi star at our policy. So at the mean field equilibrium, we will stabilize at this LMP star and the pi star. Now I'm presenting you the numerical experiment with 37 bus synthetic Oahu network. So 37 buses, each bus has 1,000 prosumers and 2,000 pure consumers. And each prosumer will have a storage with capacity of 10 kilowatt hours. And we also have different generators. And for the non-renewable one, each would have quadratic cost functions. And for the solar and the wind, the clean energy resources, they are free, but they subject to some capacity factors. So the input data look like this. The grid level wind and solar capacity factors are shown on the left-hand side. And sometimes they can produce at full capacity, sometimes they cannot. And on the right-hand side, I'm showing you the consumer, which is in the orange color, and the prosumer, which is in the blue colors, net demand shape. And the prosumer's net demand shape is defined as the prosumer's demand minus self-generated PV energy. And we run the simulation for 50 days. Each day has 12 time steps. Each step is 2 hours. And we choose PPO at the RL algorithm and run the training length is 2,400 time steps. And the results look like this. For the first 5 days, there barely no difference between learning and non-learning. But later on, in the last 5 days of the 50-day simulation, we can see the learned results. The blue curve stabilize at the same pattern for each day, and the price gets less extreme compared to the non-learning one. And we define this IMV measure for the price volatility, and we can see the learning reduce the price volatility, makes the price less extreme. And thank you very much for listening.